Bismillahirrahmanirrahim. Assalamu alaikum, dear students. I'm Arif and I welcome you all in today's session. To access the notebook for today's session, you can access course page on my personal website arifpart.me. The other way is to download the notebook file from course GitHub account arifpucit. And all the notebooks for this course are housed in this public data science repository. Well, this is the Jupyter Notebook dashboard running locally on my machine at port 8888. And here is the notebook for lecture number 7.5 of the 7th module, Overview of Natural Language Processing, for the course titled Tools and Techniques for Data Science. The title of today's session is Spam Detection Using Naïve Bias Classifier. Well, my dear students, this is the fifth session of NLP that enables computer to understand and respond to human languages in written, verbal, and sign form. In the previous four sessions, I gave you an abstract overview of the domain of natural language processing. And then we started following this generic NLP pipeline. We have covered the first three phases, namely data acquisition, text pre-processing, and feature engineering. In the last session, we discussed in detail different techniques that one can use to convert our textual data into vectors of real numbers. And the goal was that those numbers should be able to fed to the underlying machine learning algorithm. Uh, my dear friends, we did scuba diving and practically understood the two frequency-based techniques, namely bag of words or n-grams and TF-IDF. We also explored the word-to-vec word embedding technique that use neural network to transform our textual data into dense vector of 300 dimensions. And the beauty of it was that those vectors not only capture the semantic meanings of the words, but we can also perform arithmetic operations on those word vectors. Uh, and of course, in the last session, we also saw how subtracting a vector man from king and adding woman to it returns a brand new word vector that is very similar to uh, the word queen. My dear students, I strongly recommend that if you have not watched those sessions, please watch them first and then fall back to this. Anyways, today we are going to cover this fourth and the fifth phase of our NLP pipeline, and that is machine learning model building and model evaluation. We are going to start with the most basic and most common application of text classification, and that is a spam email or spam message classifier. So let us move ahead and see the agenda of today's session. Well, we will start with a quick recap of text classification, and then I will describe the probability behind Naïve bias classifier by doing a lot of toy examples using paper pencil. After brushing up your probability background, we will start with the data acquisition phase by downloading and later understanding a textual dataset that we will be uh, downloading from the UCI machine learning repository. And after doing the exploratory data analysis, we will perform text pre-processing and later text vectorization using this bag of words approach. Then comes the fourth phase, which is machine learning model building, where we will split our dataset and then we'll train our Naïve bias classifier by feeding the training dataset to it. Then I will spend a reasonable amount of time to make you understand the confusion matrix and some common evaluation metrics that are used to check the performance of different classification machine learning models. And these evaluation metrics include accuracy, precision, recall, and F1 score. At the very end, I will create a pipeline object to classify a brand new message of user's choice to be ham or spam. Well, I think this will be a long video. I strongly recommend that for a crystal clear understanding of all the six phases of a generic NLP pipeline, you should watch it from start to end. However, if you are interested in a specific subtopic, feel free to jump to it by clicking the time link in the description box below. Okay, so before proceeding any further, let us download and install all the required libraries. And let me show you the Python version as well on which I am working on this notebook, and that is 3.10.0, and the latest is I think 3.10.7 as of today. Okay, so let's start with an overview of text classification, uh, which is a in simple words is the process of assigning a class label to a given text. Uh, Today we are going to design an email spam classifier, and you all might have observed this when your Google Mail server analyze the contents of all your incoming emails and then classifies them as spam or ham. And after that, it uh, places those messages to either spam folder or maybe your inbox folder accordingly. The commonly used machine learning algorithms to classify an email as ham or spam are Naïve bias classifier, sport vector machine, convolutional neural network, and maybe the long short-term memory network. In today's session, we will do this using the Naïve bias classifier, which is a supervised probabilistic machine learning algorithm that uses the bias theorem for classification. Although in today's session we are going to understand, design, and practically write an email classifier, but let me take this opportunity to touch upon three more applications of text classification. This image on the right, where my mouse is hovering, shows the sentiments of those people. These people like uh, uh, as emojis, but of course, these sentiments can also be expressed as written text or maybe spoken text. My dear students, sentiment analysis can be as simple as detecting positive or negative sentiments and may be extended to detect specific feelings and emotions like happiness, frustration, anger, and sadness. You may come across scenarios where you are required to perform sentiment analysis on textual data, representing people's comments on YouTube videos, maybe on product reviews. Maybe you will like to carry out sentiment analysis on tweets made by people of a specific country to determine what the public think about their politicians, maybe the candidates of the upcoming elections, and later you may also like to predict the result of the upcoming elections. Well, sentiment analysis is not as simple as email classification, because in sentiment analysis you will face challenges like use of emojis, idioms, negations, sarcasm, and many more. Anyway, this is an application of text classification. The third application of text classification is topic modeling, which is a bit described in this left bottom image. Topic modeling allows us to efficiently analyze the large collections or volumes of unlabeled textual data by clustering these documents based on their contents by topics like maybe science, religion, politics, sports, business, and so on. Well, it makes an assumption that documents with similar topics use similar group of words. For example, business related documents will have words like money, market, customer, stocks, price, and so on. Out of all the existing algorithms for topic modeling, latent Dirichlet allocation and non-negative matrix factorization are mostly used. Well, in latent Dirichlet allocation, which is shown over here roughly, documents are represented by latent topics, and topics are represented by Dirichlet distribution of words. Well, most probably we will touch upon this topic modeling in some of our future session. Well, finally, language detection. This is the fourth application of text classification. A screenshot of Google Translate is shown over here, which has detected the text written in Arabic language. Can any one of you translate it? Well, yes. It says, "Welcome to learning NLP with Arif." Uh, you can add spaces lang detect to its text pre-processing pipeline for this language detection. I think that is enough for text classification. The overview of text classification. Let us move ahead. Okay, so instead of straight away jumping onto Python and start writing code for our spam classifier, let me set the stage right by describing the probability behind naive bias classifier and doing a toy example using paper pencil first. My dear students, if you have a probability background, you can of course skip this portion and straight away jump to the practical implementation part using Python by clicking the appropriate time link in the description box below. But I strongly recommend that you should brush your probability background by seeing this 10 to 15 minutes part of the video. Okay. My dear students, we all know that probability defines the likelihood of occurrence of an event. It is a ratio between the favorable outcomes and the total number of outcomes in a sample space. And its value lies between, of course, 0 and 1. The most basic probability category is marginal probability, which is the probability of an event irrespective of all other events. To understand probability at secondary school level, we start with predicting the outcomes of maybe tossing a coin and getting a head or tail, which are of course mutually exclusive events. Similarly, rolling a dice and getting a six, or maybe drawing a card from a pack of playing cards and getting a queen. So these all are the areas where you might have applied probability. Please go through with these examples for a clear understanding. Okay. After getting a fair idea about marginal probability, let us now talk about probability of two or more independent events happening together. First of all, remember that two events are said to be independent if probability of occurring of one event has no impact on the other. An example of two independent events is rolling two dices together, and naturally the outcome of one dice has no impact on the outcome of the other dice. In order to compute the probability of two independent events, we use this joint probability, and that is equal to the product of individual probabilities of those two events. So let us suppose that we have rolled two dices and want to know the joint probability of getting a 6 on both of the dices. And naturally it is equal to 1 over 6 multiplied by 1 over 6, that is 1 over 36, which comes out to be 0.0277. Please do see these examples as well, and let me move ahead. Okay, so here comes the interesting part. My students, two events are said to be dependent if they happen one after another, and the probability of first event has an impact on the probability of second event. Consider this image at the top, which shows a Venn diagram sort of picture, uh, in which the total sample space, this total area of this rectangle, uh, contains all possible weather events. Right now, we are interested in only two events, cloudy, which is shown with this cloud having this red border, and rainy, which is shown with this water drop having a blue border, and their intersection is shown with this yellow color. These two events are dependent, as the probability of clouds in the sky does have an impact of probability of rainfall. Okay, now consider this left diagram. Suppose it is given that it is cloudy outside. What is the probability that it is also raining? Over here, we need not to look at the entire sample space because it is given that it is cloudy outside. So in this equation, the conditional probability is read as the probability of rain given cloudy is equal to the overlap area of two events divided by the cloudy area. So in the denominator, instead of the entire weather sample space, we have the area of the cloud event only. So in the numerator, we have the product of probabilities of the two events, and in the denominator, we have the probability of the event that has already happened. Now let us consider this mirror question, and suppose it is given that it is raining outside. What is the probability that it is also cloudy? Over here, the conditional probability is read as the probability of cloudy given raining is equal to the overlap area divided by the raining area. Excuse me. And this is what is shown in this right diagram. Well, note that in both the cases, the numerator is same, that is probability of rain intersection cloudy, probability of cloudy intersection rain, which is of course same. But the two denominators are different. Over here we have probability of cloudy, which is the given probability in this case. Over here we have probability of rain, which is the given probability in this case. So these are the two formulas for probability of event A given B and probability of B given A. Just note the difference is there in the denominators. Well, finally, remember in case of two independent events, a probability of A given B, uh, of course, is equal to the probability of A, and probability of B given A is equal to the probability of B. I hope this is making sense. Well, here are a few examples of conditional probability. Please make time to practice these. Let me describe this example. Example 3. Well, consider this table that contains some hypothetical data of some birds in a zoo. Well, there are total of 200 birds. 90 out of them are male and 110 out of them are female. Similarly, 170 out of them have brown eyes and 30 have blue eyes. Moreover, 70 male birds have brown eyes and 20 have blue eyes. That makes a total of 90. And 100 male birds have brown eyes and 10 have blue eyes. That makes a total of 110. I hope this table is making sense to you all. Okay, now suppose a bird is selected at random. The question is, what is the probability that it is female? And naturally, this is equal to the number of female birds divided by the total number of birds, that is 110 over 200. Let's say that I am interested to calculate the probability that the bird selected is female having brown eyes. So we need to find this probability. So the count of male bird with brown eyes is 70. So it is 70 over 200. Let us now compute the conditional probability. Say I want to calculate the probability that the bird is female given that it has brown eyes. So over here we use the formula of conditional probability. So the probability of female given brown is equal to the probability of intersection of the two events divided by the probability of the given event. That is the event that has already occurred. I hope this is clear. Similarly, next I have calculated the probability of male given blue and then probability of blue given female. I hope this makes sense. Given this table, this should be a piece of cake for you all. My dear students, now let us talk about the bias theorem, which is a way to calculate conditional probability without using joint probability. Well, if you see this equation 1 and this equation 2, these are the formulas of conditional probability. And you see in the numerator of both these equations, we have a probability of A intersection B, which is a joint probability. From equation 1 and equation 2, if we move the denominator to the left hand side, that is we move this probability of B over here and over here we move this probability of A over here. So we can equate uh, these equations 3 and 4 to get this equation. That is a probability of A given B uh, multiplied by probability of B is equal to probability of B given A multiplied by probability of A. And from this we can arrive at equation 5, which is this equation, which says probability of A given B is equal to probability of A multiplied by probability of B given A divided by probability of B. And this is what the bias theorem is. That is, we are calculating the conditional probability without using the joint probability. So to compute probability of A given B, we need to know its reverse probability, that is probability of B given A, other than the individual probabilities. Well, in this formula, this probability of A given B is called posterior probability, while on the right hand side, this probability of B given A is its reverse, called the likelihood. Probability of A is the prior probability, while probability of B in the denominator is called the normalization constant, and this must be non-zero. Okay, here are a few examples that you must practice to have a clear understanding of Bayes' theorem. Let me quickly describe this example too. Well, it says consider a school in which 60% of boys play football, so probability of F is 0.6. It says that 36% of boys play cricket, so probability of C is 0.36. Well, the percentage of boys who play cricket, given that they also play football, is 40%. So probability of C given F is zero point 0.4. Now we need to compute the probability of uh, rather percentage of those who play football, given that they also play cricket. So that means we need to find this probability of F given C. So this is the formula and these are the probabilities. By substituting the values, you get the probability as 4 over 6. My dear friends, do practice the remaining examples, understand them before you move ahead. Okay, after having a clear understanding of Bayes' theorem, I think we are well equipped to understand the Naïve Bayes classifier, which is a probabilistic supervised machine learning algorithm that uses Bayes' theorem for classification problems. Well, the naiveness of this classifier is uh, that it makes an assumption that the input features are independent to each other and make equal contribution to the output label. Well, this is not the case in the real life scenarios. That is why it is called naive. Well, the three main categories of naive Bayes classifier are shown in this image. The Bernoulli naive bias is used when the values of the input features are binary, that is 0 and 1. Multinomial naive bias is used when the values of the input features are integers. And Gaussian naive bias is used when the values of input features are real numbers like age, distance, inflation, etc. Finally, the output labels of these types can be binary if you have just two classes like yes or no, ham and spam. It can be multinomial if you have more than two classes like happy, sad, and angry. The output labels can be ordinal if you have ordered classes like baby, child, teenage, adult, older. And finally, it can be multi-class where you can assign more than one label to a single observation. Okay, so let us start with a very basic example. Consider this frequency table where we have a total of 100 observations which are fruits. There is only one input feature and that is the color of the fruit, which can have three values: red, green, and orange. The output label can have two values. Uh, that is, it can be an apple or it can be an orange. So the table tells us that there is a total of 54 apples, out of which 33 are red, 20 are green, and one is of orange color. Similarly, there are a total of 46 oranges, out of which one is red, 6 are green, and 39 are of orange color. Well, since the input features are having integer values, so we will apply multinomial naive Bayes classifier in order to classify a new fruit and determine whether it belongs to this apple class or the orange class. Uh, by difference with the background knowledge we have, we can easily calculate the probability of a fruit being orange given that its color is green, as well as the probability of a fruit being apple given that its color is green. So here I have calculated those two probabilities. Once again, let me repeat that this example has, uh, in this example, we have just one input feature of a fruit, and based on that one input feature, I want to categorize that fruit as either apple or orange. And over here I am calculating the probability of the fruit being orange given that its color is green, and here is the formula, and I have substituted the values from this table in it. And over here I am calculating the probability of the same fruit being apple given that its color is green, and here is the formulation. And since the probability of the given fruit being apple is greater than its probability of being orange, given that its color is green, therefore the naive Bayes classifier will classify this fruit as apple. I hope this is making sense. Okay, so the way we have applied Naïve Bayes classifier on a dataset having a single input feature, we can easily extend it to a dataset having n input features. Note this equation and this equation, these first two equations. Well, in the second equation, we have just expanded the probability of xi given y to probability of x1 given y multiplied by probability of x2 given y multiplied by probability of x3 given y, and so on to probability of xn given y for, of course, all the entries in the dataset. Since the denominator over here remains same, so it can be removed and the proportionality sign can be injected. So this equation can easily map to this equation. Uh, this pi sign actually represent the product of these conditional probabilities, and this is of course the probability of y as such. Finally, the mathematical representation of a full-blown naive Bayes classifier with a dataset having n features x1, x2, x3, so on to xn is shown in this last equation, that is equal to or directly proportional to the maximum probability of this. Uh, Let me show you an example of this which will be more intuitive and easy for you to understand. Okay. Now consider this table having 15 records or observations. In this case, we have three input features: outlook, temperature, and humidity, and one output label named rain. Well, the input feature outlook can have two possible values, cloudy or sunny. The input feature temperature can have three possible values, cool, mild, or hot. The third input feature humidity can have three possible values, low, normal, or high. And based on these three input features for any particular record, the output label rain can have two possible values, yes or no. I hope this makes sense. Since the input features have categorical values which can be represented as integers, maybe using one hot encoding, so we can use multinomial naive Bayes over here. So this is described over here. So in this case, this is the multinomial naive Bayes classifier equation, and since we have just three features, so we have uh, written it as a product of conditional probabilities over here. So probability of y, that is this rain, given x1, x2, x3, that is outlook, temperature and humidity, is equal to the probability of y multiplied by probability of x1 given y, probability of x2 given y, and probability of x3 given y. Excuse me. Okay, so I hope this makes sense. Let's do a practical example. Let us assume that on a particular day, the outlook is cloudy, temperature is cool, and humidity is normal. And what we need to do is we need to predict whether it will rain or not on that day. Now, let us first calculate the frequency tables of the three input features from this given dataset. So these are the frequency table. This is a frequency table for this outlook column. It just tells you that how many yes and no we have for the cloudy and sunny. So this rain column comes up over here, yes and no, and these are the two values of this feature outlook. It is very similar to the frequency table that we have just created above in the previous example. From this table, the way we can create the frequency table for this outlook column, similarly we can create the frequency table for the temperature column as well. And over here we have cool, mild and hot, these three values. And similarly we can have this frequency table for humidity as well. Okay, now we need to compute the probability of y is equal to yes. That is, what is the probability that it will rain given that the values of the three features are x1 is equal to cloudy, x2 is equal to cool, and x3 is equal to normal. This is expanded to this equation. You plug in the values from these tables and you get the probability as 0.074. So this is the probability of raining given that it is cloudy, cool and normal. And similarly we can calculate the probability of not raining given that it is cloudy, cool and normal, which is equal to 0.00988. Well, my dear friends, since the probability of y is equal to yes, that is the probability of rain, that is 0.07, is more, therefore we can easily predict that it will rain on that day when the outlook is cloudy, temperature is cool, and humidity is normal. Great job done. My dear friends, I think we are now very well equipped to apply Naïve Bayes classifier on our textual data. So let us do one more example. Well, now consider this corpus of four documents, rather one, two, three, four, five, six documents. Over here we have an overall of six documents, but these are the four documents which have labels. So these first two documents are labeled positive, and these two documents are labeled as negative. Uh, and based on these four labeled data sets, we need to uh, predict these two documents. I am playing cricket and happy, I am playing cricket and not sad. So these are not labels. So given a labeled data set, we need to calculate the prior probability of the output label as we have done before. Let us first calculate the prior probability of the output label, which is shown over here for the two classes, positive and negative. The output label has two classes, positive and negative. And since in this example the data set is perfectly balanced, that is we have four observations, Two out of them are labeled as positive, two out of them are labeled as negative, a perfectly balanced data set. So the probability of positive and probability of negative both is equal to 1 over 2. Well, my dear students, before moving ahead, remember one must perform a text pre-processing on on these documents, which I am not doing over here to keep things simple. So I'm just keeping all the text. Okay, now consider these three tables, and this leftmost table shows the vocabulary of the first four documents, which is 8. 1, 2, 3, 4, 5, 6, 7, 8. So this is the vocabulary. I am happy because playing cricket, sad not. This is the vocabulary of these four documents. I hope this is making sense. Please map this. In this table, I have calculated the word frequencies, that is the number of times a word has appeared in the positive or negative documents. For example, this word happy has appeared twice in the positive documents and once in the negative documents. Let's see that. This happy and this happy has appeared twice in the positive documents, and over here it has appeared once in the negative document. So this is how I have calculated the word frequency count table over here. This is also shown over here in this formula. I hope this is making sense. Now this middle table shows the conditional probabilities of all the words in the vocabulary. For example, let me once again consider this word happy. The question is, what is the probability of this word happy given that the class it belongs to is positive? So this is what this is saying. What is the probability of the word happy given that it belongs to positive class, and that is 0.15? And what is the probability of this word happy given that it belongs to the negative class, and it is 0.08? Of course, this is the formula for which using which I have computed all these probabilities. So the frequency of happy in the positive class is 2, and that is divided by the total number of words in the positive class, which is 3. So 2 divided by 3 is roughly 0.15. And similarly over here, uh, the word happy in the negative class, the count is 1, divided by the total number of words in the negative class, which is again 13. So 1 divided by 13 is around 0.08. My dear students, please stop the video and verify the contents of all these conditional probabilities by doing calculations before proceeding any further. Let me do a bit of analysis on this middle table. Note the probabilities of the words cricket, playing, am, and I. They all almost have the same probabilities. Cricket 0.08, playing 0.08, this because 0.08. They have the same probabilities for for the positive words. And the point I want to hamper over here is that this word cricket is having the same conditional probability of belonging to the positive sentences or positive class or the negative class. Similarly, playing also have the same probability of belonging to positive or negative. And over here, roughly this I and M are also are almost same. On the contrary, words happy has a probability of belonging to the positive class as 0.15, while uh, belonging to negative class as 0.08. And similarly, this sad word has more probability of belonging to the negative class, and this not word also have more probability of belonging to the negative class. So these words happy, sad, and not, these are called the power words because they carry a lot of weight in determining the class to which a document belongs to. On the contrary, these words like cricket, playing, this am, this I, uh, uh, they have the same probabilities in both the classes, so they will not add any additional information to our model. Well, let me discuss another problem over here, and that is since this word because uh, do not appear in any document that belong to the negative class. So its probability is zero over here. In order to tackle this problem, we do Laplacian smoothing, which is done in this rightmost table. Laplacian smoothing is done by slightly tweaking the Naïve Bayes formula as shown over here. You just add a 1 in the numerator to cater for a word having zero probability, and in the denominator you add the number of unique words in the vocabulary, which is 8 in this example. Note the word because, which had zero probability earlier in the negative class, has now a non-zero probability over here. So you use this formula to compute the conditional probabilities with Laplacian smoothing to avoid any zero probability word. My dear students, once again, please stop the video, verify the values of this table by doing the calculations for a crystal clear understanding. Okay, so now let us use a Naïve Bayes classifier to classify this document, that is I am playing cricket and happy. Uh, Well, this was this sentence. I am playing cricket and happy. We have trained our model using these four sentences, labeled sentences. Now we want to predict this sentence. I am playing cricket and happy, and we want to label it. And this is what I am trying to do over here. Uh, Note that the word and do not exist in the vocabulary of our training dataset. So we do not have the word and over here. Yes. So this is the out of vocabulary problem. So one solution is that we simply drop it. Okay, anyway. So here is the probability of y is equal to positive, and here is the probability of y is equal to negative, given the sentence with these five features, that is x1 is equal to I, x2 is equal to am, x3 is equal to playing, x4 is equal to cricket, and x5 is equal to happy. Okay, so you can easily expand this formula, plug in the values, calculate the true probabilities, find out the max. And finally, the probability of this sentence being positive uh, is greater than its corresponding probability of being negative. Therefore, we classify this sentence as a positive sentence. Well, my dear students, I strongly recommend that you should also try to classify the second sentence, that is, I am playing cricket and not sad, at your own, and see if this negation in the sentence creates a problem or not. And let me move ahead. Okay, so let us now play the Naïve bias classifier on a real world dataset. Well, you can download the dataset from a UCI machine learning repository by clicking the link. Uh, well, let it be loaded. Yes, this public dataset contains uh, around 5574 SMS messages labeled as ham or spam. So I have already downloaded it, and it is there in this directory datasets SMS spam collection. Let me show its contents to you. So it is a tab separated file containing different SMSs and their corresponding labels. Okay, let us use Panda's read CSV method to load it in a data frame. Great. So it has 5572 labeled text messages which are shown over here. Uh, they are not fully displayed. So let me show you the label as well as the text message for that is at index 2. Free entry in our 2 weekly comp to win FA Cup final tickets 21st May and so on. So this appears to be spam, of course. Let me display the message at index 20 and its label. Uh, that says, "Is that seriously how you spell his name?" This seems to be a perfectly genuine message, a ham message. So this is what we just want, that our model should learn from this, and later when we give it a new text message which is not there in this data set, it should be able to classify that incoming message in real time as ham or spam. So this is what we are going to do in the remaining part of this video, inshallah. Okay, so let us add new features in our data frame. First, let me add add a new column in our data frame containing the length of every message, and this is done using the apply method on every message. And to this apply method, I'm passing the built-in length function. Let me execute it if this is making sense to you. So I have just added a new feature in our data frame, and that is the length column, which is containing the number of characters in our message. Let me add another feature, and that is the count of punctuations in our message. So once again, I'm using the apply method of the pandas data frame. This time I am passing a lambda function or anonymous function to it, and to this lambda function only one argument is being passed, that is x, which is the text of a message. And after this colon, instead of using an expression, I am passing the argument x to this user defined function count punctuation, whose definition is given over here. This count punctuation function is using a list comprehension to return the number of punctuations in that message. Note this method len over here. I hope this is making sense. Let me run it. Check this out. So we have another column, punctuation, that contains the number of punctuations that are used in this text. I have added just these two features, assuming that later they might help in classifying the message as ham or spam. So we have these four columns now in our data frame. Let me just save this in a new file, sms1.csv. Great. So exploratory data analysis. My dear friends, before proceeding any further, let us perform a bit of EDA. And for this, once again, let me load this sms1.csv file in a data frame. Excuse me. So remember, one must check the null values. There should not be null values in your data frame. So you need to handle them. Let me execute the code of these cells. We use this is a method to check out the null values under a data frame column. Uh, you can use this info method of the data frame, which tells us that there are a total of 572 entries, and for each column we have same number of non-null values. So we do not have any null values in any of our columns or records. However, if there are null values, the easiest way is to use the drop NA method, or you can use the fill NA method, whatever suits you. And I hope we have covered these in our pandas data frame sessions. Okay, let us visualize now using some graphs. First, let us see how many classes are there in under the label column. This label column of the data frame, we use the value underscore counts method. So it tells us that there are 4825 ham messages or ham labels and 747 spam. So fine, let me use this normalize argument. This normalize argument is just going to normalize these values, and we get the relative frequency of these two classes under the label column. Excuse me, gentlemen. So from this, it appears that the dataset is not very much balanced. Anyways, so over here, let me use the cat plot now. The cat plot method of cborn and display a count plot. You see the kind is count. So these bars visually display the difference between the count of the ham and the spam messages. That's great. Okay, so let's visualize the length of the text in the ham or spam messages. And for that, let me create a data frame that contains only a copy of the ham messages from the original data frame. Let me also create a df underscore spam data frame which contains a copy of the spam messages. And let me show these to you. So this is df ham, contains only the ham messages, 4825 ham messages. So this is df spam, contain only the spam messages, 747 spam messages. And let me show you a histogram. Let me use this disk plot. Good. So this disk plot method of cborn can display a histogram showing the distribution of the ham messages uh, by their length. Note that we have the length along the x-axis. Well, this graph shows that the majority of ham messages have a length of around 100 characters. Similarly, we can, of course, create a histogram of the spam as well. You see the difference between the two. So this is a histogram of the ham messages, and this is a histogram of the spam messages. And it shows that majority of the spam messages have a length greater than the ham messages. Okay, great. So let us visualize the punctuation count in a ham message. Once again, I'm using the displot method of the cborn, but this time along the x-axis, I am keeping the punctuation count. And this is for the ham messages, and this is for the spam messages. So if you closely observe these two histograms, it looks like spam messages have far less number of punctuations. So it appears that the length as well as the punctuation feature can of course be used for classification of the ham and the spam messages. Okay, my dear students, one last thing under visualization is the use of word cloud, which is a data visualization technique used for representing textual data in which the size of each word of course indicates the frequency or its importance. Well, this is a user defined function that is passed uh, a data frame, and it uses the word cloud method, this one, uh, of the word cloud module. Let me just run it. Let me just pass the spam data frame to this word cloud function of ours and see the word cloud it gives us. Great. And let me run this as well by passing this ham messages. Great. So you see the most frequently used words in spam messages in our data set are free, call, mobile, price, claim mobile, call now, and so on. And similarly, uh, the word cloud for ham messages. So far, so good. Okay, my dear students, after having a fair idea about the dataset we are working on, now we need to do pre-processing on the text, which we need to classify as ham or spam. Well, since we have already gone through this phase of text pre-processing in our lecture number 7.2 and 7.3, therefore I will not spend more time on this. So interested student can of course visit this link and see that. So let me load the data frame, the sms1.csv in this data frame. Let me show you its shape. So 5572 rows. So 5572 text messages along with their labels, length and punctuations. Well, this is a user-defined function, text pre-processing, which is passed a message and it performs lots and lots of pre-processing tasks on the message like case folding, removing digits, double quotes, square brackets, HTML tags, URLs, emojis, punctuations, and stoppers. Uh, and finally, it also do uh, either stemming or lemmatization using Porter stemmer or WordNet lemmatizer respectively. Let me just simply execute it. We have seen this in detail in our previous session. And this code cell is using the apply method on the text column of our data frame. In short, we are actually passing every message to this text pre-processing message, this function, and we are actually creating a new column in our data frame. We have done this before as well. Let me execute it. So this may take a bit of time, but not much. Okay, so this is the new column, pre-processed text. So this column is corresponding to this column, and a lot of pre-processing has been done over here. Uh, let us do the verification. Let me show you the text at the 20th index without pre-processing. It says, "Is that seriously how you spell his name?" And after the pre-processing is done, we have only three words: seriously, spell, and name. My dear friends, I have done a lot of pre-processing, and some of these might not have been required to do. I have just done this to show you. You can accordingly tailor this pre-processing function. Anyway, so let's check out the message at index 10. It says, "I'm gonna be home soon and I don't want to talk about this stuff anymore tonight. Okay, I have cried enough today." So after the pre-processing, these are the words. So we have reduced vocabulary, we have remove the punctuations, there are no URLs, no emojis, no double quotes, no digits. We have done the case folding, everything is in lower, and so on. I hope this makes sense. Well, my dear friends, now we are done with the pre-processing of our textual data. The next thing to do is of course, text vectorization. In our last session, that is lecture number 7.4, uh, we have discussed in length about different techniques that one can use for text vectorization. And let me use uh, a bag of words technique, which specifies the presence or count of a word or n-gram in the vocabulary of a corpus. And of course, we can use the count vectorizer method of sklearn. So we have two options. This option one is that we create a default count vectorizer object and then call this fit transform method on it by passing the pre-processed text column of our data frame. The next option is we use the uh, we we use the preprocessor argument of this count vectorizer method, and to this preprocessor argument we are passing the name of our text preprocessing function. And this time, once we call fit transform, note that we are passing the text column of the data frame. Over here we were passing the processed text, so both have the same impact. Anyway, so the length of our vocabulary is 7605. That is, there are 7605 unique words in the vocabulary. That is, after we have done the pre-processing. If you want to check out the feature names, you can do that. You can check out the shape of the bag of words you have got. And this is the size of the bag of word, a sparse document. 5572 by 7605, which means that this document term matrix contains 5572 rows, as there are 5572 messages, and there are 7605 columns, as there are 7605 unique words in the vocabulary. Great. Remember, this document term matrix is stored as a numpy array in sparse matrix representation. Well, we can always use this uh, two array or two dense method of numpy to convert this sparse matrix to uh, numpy nd array or to a matrix. And let me show you the sparsity of this document term matrix. Let me execute this code. We have seen it before as well. Let me just describe it. So out of a total of 42, roughly 42 million cells, only around 42,000 contains non-zero values, which means more than 99% of the values are zero, and that is the reason it is always stored in memory as a sparse matrix to conserve memory and speed up algebraic operations. I hope this makes sense. Okay, so let me describe back of words representation of an individual message. So this was the original message, and this is the pre-processed message, and this is the label. So in this pre-processed message, we have just 15 words. Uh, Moreover, the count vectorizer will leave this single character word R. So we will be left with 14 words only, I think. So there are 10 stored elements. Uh, this word mobile note that is coming three times: 1, 2, and 3. And while this word update is coming twice, and similarly, this word free is also coming twice. So that is why we have just 10 stored elements instead of 14. So we have non-zero 10 values, and we can print that as well. So this is the vector representation. Uh, just index 2396 contains 2. This index 4116 contains 3. So this 3 is actually the count for this word which is coming three times, and that is this word mobile: 1, 2, and 3. Similarly, my differences do map these uh, uh, integer values of this sentence, pre-processed sentence. Remember, I just want to tell you how good representation the sparse matrix is. You just need to store these 10 values instead of the uh, long vector of let's suppose mm, 7605 values. Okay, so now let me let me view this entire matrix as a DTM. You see, most of the values of the rows are 0. So we have a lot of zero values in the representation of every message. So this row is representing the first message. This vector is representing the second message, the third message, and so on. So these 5572 rows actually represents the 5572 messages. These are the vector representation. Every column of this document term matrix is a term or a word in corpus vocabulary whose count is of course 7605, and the values, the zero values in the cell means that this document do not have the word under this column. Otherwise, it may contain the count of that term in that document. Okay, my dear friends, we are done with converting our textual data into numbers and are ready to feed this numerical data to our machine learning algorithm. Do note that every message, irrespective of the number of words it has, is converted to a fixed size vector of 7605. So it can easily be fed to our ML algorithm. Great job done. Let's move ahead. My dear friends, we are done with the first three phases of the generic NLP pipeline, that is data acquisition along with exploratory data analysis, text pre-processing, and text vectorization. Now is the model building phase, in which we will first choose an appropriate machine learning algorithm for the classification problem at hand. We will then split our dataset into two parts, one for the training, another for the testing. And finally, we will fit the model on the training dataset. Let us discuss these steps one by one. And first of all, we need to choose the machine learning model. You can use any of these classifiers, but since this session is for Naïve bias, so we'll be using multinomial Naïve bias classifier. And because why multinomial? Because the input features in our dataset contain integer values representing the word count. Great. So my difference for every machine learning task, the first thing we do is split the dataset into two subsets. The training dataset that is used to fit or train the model, the test dataset that is used to evaluate or do the prediction. Well, there is no hard and fast rule for train test split ratio. However, the most common is 70/30. And this image describes the training and prediction steps that exist in every supervised machine learning model. Well, during the training phase, we input the features normally kept in a NumPy matrix named capital X, and the output labels normally kept in a variable named lower y. Model training actually creates a mathematical representation of the relationship between the input features and the target label. Let's do it. So x is equal to bow. The bow variable uh, already contains the bag of words vectorized representation of the input features of our dataset. So we are just assigning it to the variable x. The target variable is there in the label column of the data frame. Note that the output label can belong to two classes, ham or spam. So we have x, we have y. Let's do the split. Now it is time to use the famous train underscore test underscore split method of sklearn that is used to split arrays or matrices into random train and test subsets. The two required arguments are the input matrix X and the output label Y, which must be, of course, of the same size. The test underscore size argument specifies the proportion of the dataset to include in a test dataset. The default value of this argument is 0.25. I have kept it zero point 0.3. This random underscore state controls the shuffling applied to the data before applying the split. And of course, this shuffle is equal to true decides whether or not to shuffle the data before splitting. Well, this train test split method will return a list. The number of outputs or the number of values in this list will be equal to 2 times the number of inputs. Since we have provided two inputs x and y, so there will be 4 elements in the return list, which we have received in x train, x test, y train, and y test. Great. And here is the shape of the training and testing input data and labels. Hope this is making sense. 3,900 records for training and 1672 records for testing. Okay, my dear students, now is the time to fit the multinomial Naïve Bayes model on this training dataset. So we just need to import the multinomial NB and create an instance, named it model. So we have imported it from sklearn.naivebayes. Well, my dear students, do check out the uh, hyperparameters for fine tuning at your own. For the time being, I'm just using the default parameters, passing no arguments to it. Well, next step is simply call the fit method on this model object and pass it the x train and y train. Great. So now we have a trained model. Now it is time to test or evaluate how good this model is trained uh, using the x test and y test portion of our dataset. My dear students, in order to evaluate how well our model is trained, we use different evaluation metrics. Since our current model is a classification model, therefore we'll be using metrics like confusion metrics, accuracy, precision, recall, and F1 score. Let us first talk about the confusion matrix and create a confusion matrix for our test dataset. So we use the predict method on the model and pass it this x test. So it has given us the predictions. Let me compare it with the Y test. So this is an array of predicted values, and this is of course a series of the actual ground realities. So this prediction variable actually contains the prediction of this message as spam, and the ground reality is also spam. Great. So this is a prediction of our model on the second message, that is ham, and this is also ham. The third message prediction is spam, and the ground reality is also spam. So this looks great. We can spend hours by keep matching these values, but we need to automate it. We do need to automate it. Well, anyway, we use confusion matrix. So for to create a confusion matrix, we need to first import the confusion matrix method from the sklearn.matrix module, and to this method we pass the y test and the predictions, and it returns us a confusion matrix. So this has returned a 2 by 2 matrix as an numpy array. This is 2 by 2 because we have two output classes, ham and spam. If there are n output classes, then it would have a n by n matrix. Let me now see the confusion matrix display method. Let me use this to and pass it the confusion matrix, so it will we will have a better visualization of the same confusion matrix having four values, a 2 by 2 matrix having 1, 2, 3, 4, 4 values and 4 values over here. Before proceeding any further, my dear friends, let me describe this confusion matrix. This is just a bigger image of this same confusion matrix for better understanding. Okay, the first good thing about confusion matrix is that it is not confusing for humans, a bit intelligent humans. So a natural question comes to everyone's mind is why then it is called a confusion matrix? Well, the reason of this name is that a confusion matrix shows the statistics when our classification model get confused. Well, in this image, along the horizontal axis, we have the labels ham and spam predicted by our classifier, while along the y-axis or the vertical axis, we have the ground truth or the true labels. Since our output label has only two classes, ham and spam, so that is why it is a 2 by 2 matrix having just 4 cells. If it would be having three classes, then it would have been a 3 by 3 matrix. So since this is a 2 by 2 matrix, it shows just 4 possible scenarios. Moreover, since there are a total of 1672 inputs in our test dataset, so you can check out that these four values 14, 10, 39, 13 and 210, they all sum up to 1672. Now let us understand these values one by one. Well, the four possible scenarios says true positive, true negatives, false positive and false negatives. Over here, true means our model predicted correctly. So true means our model predicted correctly, while false means our model predicted wrong. Similarly, the second term, uh, positive and negative, are the outputs of our classifier. Since we have just two output classes, so over here I have written positive for ham and negative for spam. Okay, so now let me describe these four numbers one by one. My dear students, this 1410 in the true positive cell mean From our test dataset, there are 1410 messages which were actually ham and are predicted correctly ham by our model. You see the intersection. Actually ham, the ground label is ham and the predicted label is ham. So this is the count of true positives. Well, this 210 in the true negative cell means from our test dataset there are 210 messages which are actually spam and are predicted correctly spam by our model. Similarly, this 39 in the false negative cell mean from our test dataset there are 39 messages which are actually ham and are predicted incorrectly as spam by our model. And finally, this 13 in the false positive cell mean there are 13 messages which are actually spam but are predicted incorrectly as ham by our model. I hope this is making sense. My dear students, for a model to be good, we want to maximize the count of true positives and true negatives while minimizing the false negatives and false positives. Okay, so far so good. Okay, with these four values of the confusion matrix, we can calculate many different ratios in order to come up with different performance metrics. Let us now discuss the four most common metrics: accuracy, precision, recall, and F1 score. First, accuracy. Well, accuracy actually answers the question how often is the model correct? Well, given the confusion matrix, it can be computed by dividing the count of uh, correct answers of classifier by the count of all questions asked from classifier. And of course, in our data set, uh, it is roughly 96%, which is a good score. And this can be computing using this accuracy underscore score method by passing it the true labels which is there in the y test and the predicted labels which is there in the predictions. Let me execute it. Great. So this is 0.96. So you can just pass normalize is equal to false to get the count, that is 1620. Great. My dear students, it looks good, but accuracy does not prove to be good evaluation metrics in case of imbalanced data sets, which are very common in real world scenarios. And let me describe the accuracy paradox with an example. Well, consider an imbalanced dataset having a total of 100 messages, out of which 95 are ham and only 5 are spam. Suppose I have designed a stupid classifier that always classify a message as ham. Note this confusion matrix. You see the predicted label. It always classify every message as ham. So all the 100 messages it has classified are ham. And since 95% of the time its prediction is correct, that is 95 are ham messages, so 95% of the time it is correct, only 5% of the time it is incorrect. So a classifier that always predicts the majority class in a highly imbalanced dataset will always have a high accuracy score. So this is the accuracy paradox. So if you have understood this accuracy paradox, so let me move on to the next two metrics, which are actually precision and recall. Well, precision actually answers the question when prediction is positive, how often it matches with the ground positive. Well, it can be obtained by dividing the count of true positives with the count of predictive positives. Well, if you consider ham these ham messages as positive, which is shown in this confusion matrix, so it is 0.9908, and uh, If you consider a spam label as positive, so it will be 0.8433 by substituting these values in this formula. The same can be computed using uh, the Precision underscore score. So if you pass the POS underscore label argument as ham, so this is the value which is considering ham as positive. So this is matching with this value. And if you pass POS underscore label as spam, so the output is 0.8433, which is of course matching with this. I hope this is making sense. This is a perfect match. So after Persian, we have recall, uh, which answers the question when ground reality is positive, how often it is correct. Recall is also known as sensitivity and can be obtained by dividing the count of true positives with the count of real positives, that is TP over TP plus Fn this time. So once again, if you consider the ham as positive label, it is 0.9703, and if you consider spam as a positive label, it is 0.9417. And once again, it can be verified using the recall underscore score method. Let me execute it. See, once again, it is a perfect match. Great. My dear students, before I move on to our next metric, that is F1 score, let me discuss the limitation of these two metrics, that is precision and recall. Well, consider this left confusion matrix, which describes a situation where precision will fail. The classifier has wrongly predicted uh, 11 spam messages as ham. Note this. So in this case, if you put these values in the formulas, the precision is 47% while recall is 100%. Now consider this the middle confusion matrix, which describes a situation where recall fails. The classifier has wrongly predicted 9 ham messages as spam. So in this case, precision is 100% while recall is just 10%. And finally, this right confusion matrix describes a situation where both precision and recall will fail due to highly imbalanced dataset having only one ham message and 20 spam messages. See the values. So it appears that precision and recall values are complementary. If a model is designed to have high recall, it typically will have low precision, as is the case of this left confusion matrix. Similarly, if a model is designed to have high precision, it typically will have low recall value, as in the case of this middle confusion matrix. So in order to strike a balance between precision and recall, we move on to the next metric, and that is the F1 score. My dear students, F1 score is actually the harmonic mean of precision and recall given by this formula. Uh, Simple to understand, I think. And if you simplify it, you get this formula 2 times the precision into recall divided by precision plus recall. So remember, F1 score will be high only if both precision and recall are high, and F1 score will be low if any of the precision or recall are low. So given this confusion matrix, these are the values. If you uh, consider ham label as positive, the value is this. If you consider spam as positive, the value is this. And finally, to check out all the 4 metrics, that is accuracy, precision, recall, and F1 score, you can use the classification underscore report method. Let me execute it. Great. Do make time to verify this report with the values computed so far. It should be making sense. So precision, recall, and F1 score. So if you consider ham as positive, the F1 score is 0.98, which is 0.98 over here. If you consider spam as positive, the F1 score is 0.89, which is 0.89 over here. Great match. My dear students, this is just a kickstart on evaluation metrics. Do study this receiver operator characteristic curve at your own, which is a plot between the false positive rate along x-axis and the true positive rate along y-axis. The area under the curve represents the goodness of the model. Do click this link of Wikipedia to get a details of the confusion matrix. And I think that is enough of scuba diving in the ocean of evaluation metrics for classification algorithms. Let us move ahead. Okay, so my dear friends, we are done with machine learning model building and model evaluation, the fourth and the fifth phase. The last phase of our NLP pipeline that is left now is model deployment. Well, the actual deployment of a machine learning model in order to be accessible to the general public is described in this image. We of course need to pickle our trained or tested model and need to integrate it in a web application using Flask or Django. And later we need to deploy it on some cloud service, maybe Amazon Web Services, Google Cloud Platform, or maybe Microsoft Azure. You may also need to have a working knowledge of Docker in order to containerize your application, and maybe Kubernetes for automating deployment, scaling, and maybe management of your containerized application. My dear students, I will be spending one or two separate video sessions on this deployment phase, inshallah soon. And for the time being, let's keep things simple and create a sklearn pipeline object. An sklearn pipeline object that can take a brand new message and filter it as ham or spam. I think this can be done in 5 minutes. Well, my dear students, a scikit-learn pipeline is nothing but a sequence of transformers. Sequence of transformers like pre-processing, vectorizing, followed by maybe an estimator like multinomial NiFi's, all assembled and executed as a single entity. And this is shown in this image. Well, remember here, transformer is something that implements a fit and transform function, while the estimator, like multinomial NB in our case, have a fit as well as the predict function. So simply speaking, you input a plain text message to this trained pipeline and it will do all the necessary transformations and predict it as ham or spam. I think enough of theoretical background. Let us make our hands dirty by creating a pipeline of our own. So let us read and load the dataset in pandas data frame. Assign the unprocessed text, this text to X and the output label to Y. And let me do a train test split as we have done before. So here comes the new part, this thing, where I'm creating a pipeline object. Well, you can pass any number of transformers and finally an estimator as a list of tuples. Uh, the first value of this tuple over here is a string that names the transformer, and the second is the transformer object. In this example, I am passing just one transformer, and that is count vectorizer, and one estimator, and that is multinomial NiFi's. Well, as a side note, you can always write your own transformers. Let me just execute it. Great. So we have a pipeline object now. Now we call the fit method on this pipeline object by passing it the x train and y train. Let me execute it. So now this pipeline object is ready to predict the input messages. Let's try it. Let me create a sample message that is, good morning Arif, can you call me? And Let me pass this message to the predict method of the pipeline that we have created. So it has evaluated it as ham, and of course this appears to be ham. Let me create another message, that is call me now and get a free mobile. This seems to be a spam message. Let me pass this message to the predict method of the pipeline, and it has successfully evaluated as spam. Okay, Alhamdulillah, we are done with today's learning. This was a long session, of course. My dear friends, if you have liked it, please subscribe my YouTube channel and share it with your friends. I wish you all the best, happy learning, and Allah Hafiz.